In the previous video, I talked about how we can calculate mechanism loads using the static analysis method and the energy method. In this video, I'm going to go through calculation of mechanism loads again using both of the methods, but with a bit of a more complicated example. So in this particular example, we have a lever mechanism with a fixed actuator. So the actuator can't move and it's positioned at L on 2 from the pivot point A. We also have the lever which pivots about A, and at the end of the lever we have a force F applied, and that's applied at the distance L from the pivot point A. So what we'll do first is use the statics analysis method to work out what our actuator force is. Okay, so as always with the statics analysis method, we start with a free body diagram. So let's draw that up now. So we have a line to represent our lever, and let's draw in the geometry components. So we can represent the rotation of the lever by the angle alpha. We've got the pivot point A. At the end of the lever, we have the distance L, as we talked about before. And also we have the roller, which acts off at a distance of L on 2. So let's draw that in. Now we will draw in our forces. So again, at the end of the lever, we've got the force F, and at the middle of the lever, we've got the actuator pushing it up. And because it's a roller, we have a force directed normal to its contact point with the lever. So we actually have a component of force in the vertical direction, and that's actually our force FA, so the actuator force. Then we have some reaction in the X direction. Fortunately, from geometry, we can work out what this angle is between the actuator force FA and the reaction force Rx. And that's actually just alpha. So we'll be able to work out Rx in terms of the actuator force. So a few other things we'll need to know, and that is the distance between where the actuator applies the force and the pivot point, and let's call that distance S. We will also need to know the distance perpendicular from A to where the force is applied, and that is actually given by L cos alpha, and we can work that out from trigonometry. Okay, we really have got all we need now to work out what the forces are. So let's do the sum of the moments about pivot point A. In actual fact, why don't we draw out the diagram for the actuator force. So we've got FA as described, Rx. We've got some reaction from the roller, and it's constrained by the angle alpha. So we can say that tan of alpha is equal to Rx on FA. Therefore, Rx equals FA by tan alpha. Okay, now let's go ahead and work out what the sum of the moments about pivot point A is equal to. So we'll take, by convention, anti-clockwise as positive. Sum of the moments about pivot point A is equal to, and it's equal to FA multiplied by the perpendicular distance to pivot point A, which is equal to L on 2. And that is acting in the positive direction about pivot point A. So it is positive. And then Rx is also acting in the positive direction about A. And we have the perpendicular distance from A as S in our diagram. So let's just work that out again. So let's draw this triangle up to work out what that value of S is equal to. So we've got L on 2 and S with the angle between it being alpha. So tan of alpha equals S on L on 2. So S equals L on 2 by tan alpha. Okay, so going back to some of the moments, we can say plus Rx times by the perpendicular distance from pivot point A to where Rx is applied, and that is S, which is L on 2 tan alpha. And finally, there is one more force, and that is force F. That's actually applied such that it causes a clockwise direction moment about pivot point A. So that'll be a negative moment. So negative F times by the perpendicular distance from pivot point A to the force F, which is L cos alpha. That is all equal to 0. So now we can rearrange all of this so that we can determine our actuator force FA. So FA by L on 2 is equal to FL cos alpha minus Rx L on 2 tan alpha. This is probably a good time now to substitute in our value of Rx that we worked out earlier. So remembering that we had a relationship between the normal force, and it was applied at a known direction alpha, so that we could work out the relationship between Rx and FA. And we worked it out to be Rx equals FA of tan alpha. So let's substitute that in. So FA L on 2 is equal to F L cos alpha minus Rx. Oh, it's time to substitute that in. So here we go. So Rx is FA tan alpha, put that in brackets, times by L on 2 tan alpha. So we can calculate that out further. FA L on 2 is equal to FL cos alpha minus FA L on 2 tan squared alpha. Okay, so now all we have to do is rearrange again and invert 2 on L to bring it on the other side. So it equals 2 on L, and we can factor out the L for this equation on the right hand side. So L F cos alpha minus FA on 2 tan squared alpha. So of course we have the L's cancelling each other out. And here we go, we can rewrite it all up as FA equals, and we've got 2 times F cos alpha minus FA tan squared alpha. Now all I need to do is bring the FA over to the other side. So FA 1 plus tan squared alpha is equal to 2 F cos alpha. So finally, FA equals 2 times F cos alpha divided by 1 plus tan squared alpha. And that gives us our relationship between FA and F. So that's using the static analysis method. Okay, now let's consider the energy method. So if we draw up that diagram quickly again, we had F, it was acting at the end. We had some reaction from the roller. We have the pivot point A, and let's put in the angle alpha again. We had alpha. We also worked out what S was equal to, and we worked out, well, we haven't worked out yet, but we can work out what this height H is equal to. So if we remember back, we had L being the distance of, or the length of the link, and we had the distance between where the roller applied its force being L on 2. Okay, so before we go further with the energy method, let's work out a few relationships. So we can see the value of H is equal to L times by sine of alpha. So that's straight out trigonometry. And we worked out what S was equal to before. And S is equal to L on 2 tan of alpha. That's because tan alpha equals S on L on 2. We worked that out from trigonometry. So these are our two key relationships that we need for the energy method, because what we want to do is work out the distance that the forces traverse, so that we can work out the energy that's actually expended. So with the energy method, we say that the energy into the actuator equals the energy lifting the load to height H. Okay, so we can write that as an equation, as we did in the previous video. So the integral of FA ds, so this is the actuator force in the direction of S. So remember in the free body diagram, we worked out that there was a component FA, and that's the actual component of force applied by the actuator. And the energy is equal to that force times by the distance that it's traversed, ds, or collectively. So that's the integral of FA ds. And likewise, that's all equal to F, integral of F by dH. And so H is in the same direction as the force F, S is in the same direction as the force FA. As we said in the last video as well, this equation that we've just written out for equating energy, and we can do that by conservation of energy, is the same as the equation FA ds equals F dH. So this now becomes a differential equation which we can rearrange. So FA equals F times dH by ds. And dH by ds is something that we can find because we have H, which is shown here, and we've also got S. But the only thing is, both H and S are in terms of alpha. So what we can do is we can use the chain rule to rewrite dH by ds. So FA equals F by dH by d alpha times by d alpha by ds. And you can consider that to be the same as the previous equation, because if the d alphas cancel out, you've just got dH by ds. Okay, so now let's rewrite what h is. So h is equal to L sine alpha. S is equal to L on 2 tan alpha. So all we really need to do now is work out what dH by d alpha is. Well, that's the first thing we need to do. And that is because we want to work out what this part of the equation is for FA. Okay, so dH by d alpha is simply the derivative with respect to alpha of L sine of alpha. And the derivative of sine of alpha is just cos of alpha. So dH by d alpha is equal to L cos alpha. Okay, so we can do a similar thing to work out our other derivative that we need, and that's d alpha by ds. So we've got an equation for s, so we can actually work out what ds by d alpha is equal to. And that's purely the derivative with respect to alpha of s, which is equal to L on 2 tan of alpha. Now, the derivative of tan alpha with respect to alpha is actually 1 plus tan squared alpha. So ds by d alpha becomes L on 2 times by 1 plus tan squared alpha. Okay, but we're not finished there, because what we actually needed was d alpha by ds, and what we've got is ds by d alpha. So to work out what d alpha by ds is, all we have to do is take the reciprocal. So d alpha by ds is equal to 2 on L 1 plus tan squared alpha. Okay, so now we've really got everything we need to work out what f of a is. So as we saw before, f of a equals f by dH by d alpha by d alpha by ds. So now all we have to do is substitute that all in. So f of a equals f dH by d alpha. Well, that is equal to L cos alpha. So let's write that in. L cos alpha. And d alpha by ds, well, that's equal to 2 on L 1 plus tan alpha. So if we write that in, we have 2 on L 1 plus tan squared alpha. So we can see now that the lengths cancel out, and we're left with the equation for FA, which is equal to 2 times F times cos of alpha, all on 1 plus tan squared alpha. And actually, this equation is identical to the equation that we found using the static analysis method. So both the static analysis method and the energy method provided us with the same result for the value of the actuator force. So again, as with the previous video, there's two different methods, and the static analysis method is very good for simple type problems. But as the problem complexity increases, the energy method is really an elegant way to solve your mechanism forces. Thank you.